Hello dear students, in today's lecture we will continue our discussion on understanding the particle motion in an isolated, uniform and static magnetic field. In the last lecture we have derived Vx, Vy and Vz. So, Vx is Vx0 cos omega t plus Vy0 sin omega t. Vy is minus Vx0 sin omega t plus Vy0 cos omega t. Vy is minus Vx0 sin omega t plus Vy0 cos omega t, and Vz is Vz0. The meaning of these relations is that Vx and Vy will continue to decide the perpendicular component of the velocity, and Vz will remain a constant under the influence of magnetic field. Right. This is pretty much known to us. So, we have the magnetic field and V perpendicular and V parallel. V perpendicular results from Vx and Vy. Let us say Vx square plus Vy square will be equal to V perpendicular, and V parallel will be the velocity which is along the magnetic field. Right. So, the magnetic field is Vz. Right. Now, if we combine, we have already done this, right? Vx square plus Vy square turns out to be Vx0 square plus Vy0 square. We can call this as the V perpendicular square. Now, the velocity is resembling an equation of circle. So, the motion is circular motion in reality. We also realized what is the angular frequency that is associated with this circular motion. Let us go ahead a step and find out how will the position will look like. Let us say if I have to write x of t, then I have to integrate this velocity, right. So, we have to integrate Vx dt, which will be something like this. X is equals to Vx0 sin omega t divided by omega plus Vy0 minus cos omega t divided by omega. This is x. And similarly, we can write y as Vx0 cos omega t divided by omega plus Vy0 sin omega t divided by omega. Right. So, there are some constants. So, I am neglecting all the constants. So, x and y will look like this. Now, more importantly, so what can we do about x square plus y square? Ultimately, this will be the trajectory of the particle. X square plus y square will tell you how the particle is moving in the xyz plane, right. So, we can find out x square plus y square just squaring and adding these two things. So, I will write it anyway. X square plus y square is V0 x square by omega square. Okay. So, I have been calling Vx0, right. So, let us say we write it as Vx0 to avoid any confusion, and this is both the things are same, the way we have considered it at least. Sin square omega t plus cos square omega t plus Vy0 square by omega square times sin square omega t plus cos square omega t plus of course the remaining terms. What are the remaining terms? You see, what I have done is I have taken this expression, squared it, taken this, squared it, and added both. So this is a plus b square, a minus b square, and this is a plus b square. So adding all these terms, we can realize easily that all the remaining other terms will get cancelled. Will get cancelled, and we have x square plus y square is vx0 square plus vy0 square divided by omega square. So we can write x square plus y square as equal to v perpendicular square by omega square, because vx0 square plus vy0 square is equal to v perpendicular square. Now let us try to understand the meaning of this expression. This is the result of the entire discussion that we had. As the particle moves in a uniform magnetic field, its position along x and y will be equal to ratio of the perpendicular component of velocity and the angular frequency, right? So what kind of motion? This is an equation of circle actually, right? So this resembles something like x square plus y square is equals to r square. That means this circular motion is executed by the particle with a radius of v perpendicular by omega. So this is distance, right? V perpendicular velocity by angular frequency. If you take that ratio, you will realize that the dimensions are of the length, right? So this is the radius of the gyration. So we call this as RL. What is this? This is the radius of gyration, right? Now we know that the particles are executing circular motion. So if you look at in this plane, it will appear to be slanted, but it is circular motion, right? Now we have to understand, we are yet to understand how will the particle, let's say an electron move and an ion will move. Will they move in the same direction? Will they move with the same velocity? Will they move with the same angular frequency? Will they move with the same radius and all these things, right? So, but for now we have established that the radius of gyration will be v perpendicular by omega, right? So we know that omega is qb by m, right? qb by m. So using this, we can write the radius of gyration as m v perpendicular by qb. The radius of gyration is m v perpendicular by qb. So here we can understand few very important conclusions. One, depending on the mass, the radius of gyration will change, and depending on the strength of the magnetic field also, the radius of gyration will change. And looking at the frequency, omega is qb by m, right? So we can write the frequency 2 pi fc is equals to qb by m. So if we know the frequency, we can know the time period is 2 pi, the time period is 2 pi by omega, which is 2 pi m by qb, right? So most importantly, omega is qb by m, the time period is 2 pi m by qb, the radius of gyration is m v perpendicular by qb, right? Or if you want to write the frequency as it is qb by 2 pi m. So the dimensions are for omega, which is radians per second. For time period, this is seconds, radius meters, and this is hertz, right? So this is the conclusion of the entire discussion that we had so far. the particle's motion is governed or characterized by these 4 parameters. Now, of course, the magnetic field's effect is realized only in the x and y components of velocity. The z component of the velocity will remain a constant with respect to time, right? So, Vx and Vy are referred to as the perpendicular components of the velocity, and Vz is the parallel component. Now, there is some more discussion that is related to this topic, where we will try to establish how the particle's trajectory can be drawn given the type of magnetic field. Okay. So, for that we have to understand the coordinate system, or we have to be clear how we are defining the coordinate system and which particle will rotate in which particular direction, right? Okay, let us say we define what is called as the right-handed coordinate system. Right-handed coordinate system, you define it, the easiest way to define it is, let us say you have this x, y, z. In the right-handed coordinate system, x, y, z are named such that they are following as per the curl of the fingers of your right hand. So, if you take your right hand, so this is the way, right? This is the counterclockwise direction, C, C, W, counterclockwise direction. So, you write the coordinates x, y, and z in the counterclockwise direction, and what it means is you are writing x bar cross y bar is equals to z, x cap cross y cap is equals to z cap. This is the rule that this coordinate system will follow. Now, the z coordinate is drawn like this, but if you want to visualize this z coordinate, z axis is actually coming right out of the page. Okay. So, the best way to draw this is like this. This is your x, this is your y, and this is your z. This becomes x cap, y cap, and z cap. Now, you can choose your x to be anything else. You can choose it to be in any other direction. X is comfortably drawn generally in this way. You can write x, y, z. Now, this is your plane, and z axis is coming out of the page. Okay. So, like that you can choose this to be x, this to be y, and this to be z. So, the sense of rotation is important here. So, this is the right-handed coordinate system, right? So, exactly opposite will be valid for the left-handed coordinate system, right? So, here z cap is out of page. What are we trying to understand? We are in the process of drawing trajectories of electrons and ions when they are subjected to a magnetic field, right? Now, using this right hand thumb, we can also indicate what will be the direction of the charged particles, but the sense of rotation, the sense of gyration needs to be understood more thoroughly. So, further we have to understand the coordinate system, and in any given coordinate system, what is this sense of rotation? How does it correspond, right? Now, we define the angle phi always with respect to the positive x-axis. So, this becomes phi cap, or phi, or this direction in which phi increases becomes phi cap. The unit vector always denotes the direction in which it is increasing at the fastest. Okay. The left-handed coordinate system can also be drawn easily. Let's say we take this. So, in the left-handed coordinate system, the sense of x, y, z will follow the clockwise direction, meaning x cap cross y cap will be equal to minus z cap. This is the difference, right? So then I have to take this as, let's say, this as x. If I have to take this as x, then I have to take this y and this is z. And the unit vectors will be x cap, y cap, z cap. You see here, the sense of rotation is like this. And here the sense of rotation is like this. The easiest way to denote the left-handed coordinate system, this is the left-handed coordinate system. If you choose your axis to be like this, this is your x. Now here we cannot draw a dot, it has to be like this. Okay, so this is x, y, z. The z cap is going into the page. That is the basic idea, right? Now here again we define the phi, the value of phi with respect to the positive x-axis, right? So you know how it is defined, how the orientation is, right? So just to conclude, the right-handed coordinate system indicates the assigning of axis x, y and z in the counterclockwise direction, and the left-handed system assigns in the clockwise direction. In the right-handed system, x cap cross y cap gives you z cap, and in the left-handed coordinate system, x cap cross y cap gives you minus z cap, right? Once we establish this, right, once we establish this coordinate system, now we will make a generalized statement saying that if this coordinate system is what you have taken, and if you have denoted the angle phi like this, then the electron will rotate like this, ion will rotate like this. Okay, all these things can be deduced by using the simple left hand or right hand rule, but then to be able to draw them, we need to have a more thorough understanding. Just draw the axis, and then once you draw the axis, you should be very confident to say that the electron will of course rotate like this and ion will rotate like this, right? Because they are circularly rotating each other, right? Now let us say, for reference, from here onwards we will take the, let's say, the right-handed coordinate system where you have x here, y here. So we will take a right-handed coordinate system in which the z-axis is out of the page, and we will assume that the magnetic field is along z-axis. In this case, like I said, the angle phi, which quantifies the magnitude of rotation at any given point of time, is represented with respect to the positive x-axis. Okay, so in that case, we know that omega c is minus qb by m, right? So for an electron, which is a negative charge particle, omega c becomes positive, which is qb by m. Now remember this. So if the charge is negative, then the rotation will be such that phi is increasing. Just remember, you draw this coordinate system, and if it is a negative charge particle, the rotation will be such that the phi, value of phi, is increasing, right? So what I have drawn is the particle is rotating like this, where the angle phi is increasing as the particle goes, right? So this is valid for an electron. That means increasing phi will be the sense of rotation for an electron, right? And if you take the exact opposite for an ion, it will be omega c will be negative, or it will be minus qb by m, and an ion will rotate such that phi is decreasing, right. So, if I redraw the coordinate system, this becomes x, this is y, and this is z, right. Now, the ion will exactly, let us say this is phi, right. So, the ion will rotate such that the angle phi is decreasing. So, this will be like this. This is for the ion, right. So, the rotation will have a characteristic radius which is m v perpendicular by qb. Now, if you consider the two particles, an electron and a singly ionized species atom something, then you have the charge as constant. So, the radius of gyration will be more when the mass of the particle is more. So, if you put that to perspective, it will be something like this. Okay. So, the electron will rotate like this and ion will rotate like this. So, the ion is having a larger radius in its circular motion, right. So, this is the right handed coordinate system. The thumb is pointing the z axis. This curl is indicating how x, y should be taken in the CCW direction, right. Now, once we know this, we can draw the trajectory of the particles accordingly. Now, there is one more very important thing here. As the particle is rotating around the center, okay. So, this point around which the particle is executing this circular motion is called as the guiding center. And guiding center is very important in order to understand the particle drifts. Okay. Okay. So, now we can write Vx as V perpendicular cos omega ct plus psi, let us say. Vy is V perpendicular sin plus psi, and Vz is V parallel. Okay. Omega ct or omega c is nothing but the omega that we have been referring to, which is the angular frequency, right. Now, this is the trajectory of the particle. What is psi? Psi is just an initial phase angle which defines the orientation of the particle when at t is equal to 0. So, that means if you have this, the particle is at t is equal to 0, the particle is here, and if it is an electron, it will go like this. If it is an ion, it will go like this, given that x and y are oriented in this direction. So, it will gyrate like this. Electron will gyrate exactly in the opposite direction. So, V perpendicular is square root of Vx square plus Vy square. This follows directly from the equation. Now, in order to appreciate this equations of motion, we can draw the trajectory and then we can realize how easily it represents, right. Now, let us say the particle is rotating in a circular motion, okay, around. We take the magnetic field to be going into the page, then in that case, the particle is rotating, of course, in a circular plane, and if it is a positive ion, you can apply this xyz coordinate system and figure out what is the sense of direction. So, this will be the velocity, and the particle will always experience a force which is V cross B. You see, the magnetic field is going in, the velocity is in this direction, right. Then the magnetic field is in this direction, the velocity is in this direction. So, you have the other force, the Lorentzian force is exactly acting perpendicular to the velocity as well as the magnetic field. So, this is how it is, right. So, the magnetic field is inside, velocity is towards this, and the force is in this direction. So, as the particle rotates, always the velocity vector will be tangential to the trajectory. The magnetic field will keep pointing towards into the page, and this thumb, which is the direction of the force, is always pointing towards the center, right. So, this is the Lorentzian force. Now, the particle's charge is, let us say, q. So, at any point, the force is acting inside, the velocity is like this, right. So, the particle is not falling into the magnetic field, right. So, there is a balance. What is the balance? The centrifugal force is balancing the Lorentzian force. So, m v square by r, v perpendicular square by r is q times v cross b, or we can simply write q v b because we have taken a perpendicular configuration. So, we can write r, from here also we can write, I have indicated a minus to say that these two forces are opposite to each other, mv perpendicular by qb, right. So, we have arrived at the same factor. The radius of gyration is equals to mv perpendicular by qb. This radius is called as the radius of gyration. The radius of gyration. So, we will continue this discussion in the next lecture, where we will try to understand some more aspects of this gyration.